Good day, esteemed researchers and curious minds tuning in from around the globe.
Today we delve into the fascinating world of robotics and language models with our study, VoxPoser, Composable 3D Value Maps for Robotic Manipulation with Language Models.
We explore how we can harness the power of large language models to guide robots in the real world, breaking away from the constraints of extensive data collection and manual designs. Stay tuned as we unravel how VoxPoser paves the way for efficient language-guided robotic interactions.
The crux of our research lies in grounding abstract language instructions in robot actions.
We leverage the knowledge of large language models or LLMs to achieve this.
Previous works in this field have used lexical analysis and predefined motion primitives. However, these methods face a significant bottleneck due to the lack of large-scale robotic data.
Our problem statement is clear. LLMs are impractical for directly outputting control actions in text.
Our aim is to enable robots to act in the real world without the need for extensive data collection or manual designs for each primitive.
This is a significant step forward in the field of robotics and language models, and we believe it opens up a new avenue for exploration and innovation. Our research introduces a novel method called VoxPoser.
This approach leverages large language models or LLMs to extract affordances and constraints. It then uses this information to compose 3D value maps in the observation space, guiding robotic interactions.
This process involves inferring language-conditioned affordances and constraints, and creating dense 3D voxel maps that ground them in the visual space.
Now let's talk about the technical results. VoxPoser demonstrates zero-shot generalization for open-set instructions with open-set objects. This means it can handle a wide variety of tasks without prior specific training.
Furthermore, we found that VoxPoser can benefit from limited online interactions.
This allows it to efficiently learn a dynamics model that can handle tasks involving contact-rich interactions. This is a significant step forward in the field of robotics as it reduces the need for extensive data collection and manual designs for each individual task.
Our research focuses on a fascinating problem. How can we ground abstract language instructions in robot actions? Imagine a scenario where you tell a robot to set up the table.
How can we translate this instruction into a sequence of physical actions that the robot can perform?
The motivation behind our work is to leverage the vast knowledge that large language models or LLMs have internalized.
These models have learned to represent the world through language, and we believe this knowledge can be used to enable robots to physically interact with their environment. The figure you see here provides an overview of our approach, which we call VoxPoser. This approach extracts affordances and constraints from LLMs to compose 3D value maps in observation space, guiding robotic interactions.
This way we can bypass the need for laborious data collection or manual designs for each individual primitive. In essence, we're teaching robots to understand and act upon language instructions, opening up a world of possibilities for human-robot interaction.
The importance of the problem we're addressing cannot be overstated. It has significant implications for the development of intelligent autonomous systems. Existing approaches have relied on lexical analysis and the decomposition of instructions into a textual sequence of steps.
They also depend heavily on predefined motion primitives. However, these methods have their limitations.
A major bottleneck is the lack of large-scale robotic data. It's also impractical for large language models, or LLMs, to directly output control actions in text. The specific problem we're addressing here is how to leverage the internalized knowledge of LLMs at the fine-grained action level for robots. This is a crucial step towards creating more capable and autonomous robotic systems.
Our proposed solution, VoxPoser, is a novel approach that extracts affordances and constraints from large language models, or LLMs, to compose 3D value maps.
This method leverages the power of LLMs for open-world reasoning and visual language models, or VLMs, for generalizable visual grounding. This approach allows us to guide robotic interactions in a more efficient and effective manner. One of the key improvements of VoxPoser is that these value maps serve as objective functions for motion planners.
This means that the robot can directly synthesize trajectories to achieve the given instruction, without the need for additional training data for each task or for the LLM.
This is a significant step forward in the field, as it reduces the need for laborious data collection or manual designs for each individual primitive. In essence, VoxPoser is a promising solution that combines the strengths of language and visual models to enhance the capability of systems. It's a testament to the power of AI in transforming the way we interact with the physical world. Let's delve into the heart of our research, VoxPoser. This innovative method harnesses the power of large language models or LLMs to guide robotic interactions. The beauty of VoxPoser lies in its ability to use LLMs for open-world reasoning and vision language models or VLMs for visual grounding.
The goal?
To enable physical robot actions without the need for extensive data collection or manual designs.
Now let's talk about the role of LLMs in VoxPoser. These models are adept at inferring language-conditioned affordances and constraints.
They can compose dense 3D voxel maps, grounding them in the visual space.
For our research, we've utilized GPT-4 from OpenAI API as our LLM. This combination of LLMs and VLMs allows VoxPoser to create a model-based planning framework that directly enables physical robot actions. In our research, vision language models, or VLMs, play a crucial role in the operation of VoxPoser.
To begin, an open vocabulary detector known as OWLVET is used to obtain a bounding box.
This bounding box is then processed to generate a mask, which is tracked using a video tracker called XMEM.
By combining the tracked mask with RGBD observation, we can reconstruct the point cloud of the object or part in question.
Moving on, let's delve into the composition of value maps in VoxPoser.
We define several types of value maps, including affordance, avoidance, end-effector, velocity, rotation, and gripper action.
Each of these map types is managed by a different language model program or LMP.
To enhance these maps, we apply Euclidean distance transform to affordance maps and Gaussian filters to avoidance maps. This intricate process allows us to create detailed and accurate value maps that guide the robot's actions. In our research, we've developed a unique approach to motion planner optimization within our system, VoxPoser. This optimization process primarily considers two types of maps, affordance and avoidance. These maps provide crucial information about the environment and the robot's interaction with it.
The cost map, a key component of our optimization process, is computed as the negative weighted sum of these normalized affordance and avoidance maps. This calculation allows us to effectively guide the robot's actions in the environment.
Once we've synthesized a 6D OF trajectory, our system doesn't stop there. It continually replans a new trajectory at a rate of 5 Hz. This dynamic approach ensures that our system can adapt to changes and maintain optimal performance.
This is just one of the ways that VoxPoser is pushing the boundaries of robotic interaction.
Our research has yielded some key results with VoxPoser.
Firstly, we've seen remarkable zero-shot generalization.
This means VoxPoser can adapt and execute a wide range of tasks without any prior specific training. This adaptability and versatility open up exciting possibilities for real-world applications where tasks are not predefined and can vary greatly.
Secondly, VoxPoser has shown the ability to learn from limited online interactions.
This means that even with minimal interaction with the environment, VoxPoser can improve its performance and adapt to new tasks. This capability to learn and adapt in real time enhances its performance over time, making it a dynamic and evolving solution for robotic manipulation tasks.
Our ablation studies have validated the effectiveness of VoxPoser in both simulated and real-world environments.
It has shown robustness and versatility in handling a variety of tasks across different settings. This is a testament to its ability to ground to abstract language instructions in robot actions, making it a promising solution for real-world applications. Moreover, VoxPoser is not limited to simple tasks. It has demonstrated its capability to efficiently learn and handle more complex tasks. This opens up the potential for its use in more advanced applications, expanding its range of use cases. This efficiency in learning challenging tasks is a significant step forward in the field of robotics, paving the way for more sophisticated robotic interactions in the future.
Let's take a moment to reflect on the key contributions of this research.
We introduced VoxPoser, a novel approach that grounds abstract language instructions in robot actions. This is a significant leap forward as it leverages the internalized knowledge of large language models or LLMs.
What makes VoxPoser stand out is its ability to enable robots to act in the real world without the need for extensive data collection or manual designs.
This is a game changer in the field of robotics and AI.
Now, if you look at the figure, you can see a visualization of VoxPoser's performance in real-world environments.
It showcases how the system guides the entity of interest towards target positions, demonstrating its ability to handle a variety of tasks and adapt to different scenarios.
This is a testament to the versatility and adaptability of VoxPoser.
In conclusion, VoxPoser is not just a theoretical concept, but a practical solution that has the potential to revolutionize the way we use robots in our everyday lives. Our research has made significant strides in the field of robotics and language models. We've demonstrated how large language models, or LLMs, can infer language-conditioned affordances and constraints, and compose dense 3D voxel maps, grounding them in visual space. This has led to the development of VoxPoser, a system that leverages the knowledge of LLMs to guide robotic interactions.
The key takeaways from our work are manifold.
Firstly, we've shown that LLMs can be used to infer language-conditioned affordances and constraints, providing a new way to interpret and execute complex instructions. Secondly, VoxPoser enables physical robot actions without the need for extensive data collection or manual designs for each individual primitive. This is a significant step forward in the field of robotics.
Furthermore, VoxPoser has shown the ability to learn a dynamics model from limited online interactions, demonstrating its adaptability and potential for real-world applications.
We've validated VoxPoser for real-world manipulation tasks and its generalization in simulation, proving its robustness and versatility.
We've also enabled the learning of more challenging tasks, pushing the boundaries of what our robots can achieve.
Lastly, we've analyzed the source of errors in our system and identified potential improvements, showing our commitment to continual refinement and advancement in this field.